we are going to talk about diodes, BJTs, and MOSFETs. And this is the second take of this lecture because I gave it once and I thought it was not so great, and so I'm doing it a second time. So this is take two. So we're going to start with diodes because they're a pretty fundamental semiconductor device. The symbol for diode is going to be this. We would call this the anode, and we call this end the cathode, and it's a cathode with a K for whatever reason. The general principle of a diode is that it will permit current flow from anode to cathode, but it will prevent current flow from cathode to anode. So the basic construction of a diode internally is it's comprised of two different semiconductor regions, and they're comprised usually of silicon. You know, those are your garden variety diode is comprised of silicon that's been doped with, or which means they've sprinkled impurities into the silicon to form either a surplus of electrons or a surplus of electron holes or a deficiency of electrons. So in the case of a surplus of electrons, so you've added some dopant that allows there to be like a sea of electrons in a sense. We would call this an N-type doped silicon. And you can, I'll draw a bunch of minus signs. And then we would put this up against the opposite, which would be a P-type silicon, where we've doped it with some impurities that allow it to have a slight a surplus of electron holes. And so right at the junction where these two parts meet, this PN junction, you have this inversion layer where as you can imagine, initially there's sort of there's an attraction between the holes and the electrons, and the electrons and holes right at the PN junction switch places, and this sort of cancels out the electric field that exists, you know, between the holes and the electrons. So they reach this sort of equilibrium point. Now, this would be the anode of my diode, this would be the cathode of my diode. And if I want to pass a current through my diode, I first need to overcome I need to overcome this voltage, or I need to apply enough electric field so that this inversion layer flips. So I need to apply enough electric field to start pushing more holes into the N region and pulling more electrons into the P region. And so this, this ends up becoming some voltage that I have to apply across the diode in order to pass a certain amount of current. And there's actually a handy equation that you can use to find this, and it's known as the Shockley diode equation. Shockley diode equation. And it says that the current through our diode, ID, equals this parameter called the saturation current times E BT over N V thermal minus 1. And so what we're interested in here is the relationship between the diode current, I sub D, and the diode voltage, VD. And everything else here, you can effectively consider it to be a constant. You know, the saturation current is some property of the semiconductors, and the quality factor N here, it's also a quality of quality of the semiconductors. V thermal here is actually dependent on Boltzmann's constant. It happens to be Boltzmann's constant times temperature divided by the charge on an electron, which at room temperature is about 25 millivolts. So that's just a little fact that's good to know. V thermal is at room temperature about 25 millivolts. So what I want to get at here is that the relationship, you know, between VD is equal to, you can see that it's going to be equal to some natural log of at some point diode current and stuff. So we have this logarithmic relationship between diode current and forward voltage of the diode. So at very small current, the forward voltage across the diode is small, right? If this were current and this were voltage, you can expect some relationship kind of like this, where this is, with silicon diodes, it happens to be about 0.7 volts. And you know, the current, it's going to vary depending on your diode. So it's not useful to really talk about. But what I'm getting at is that for very small currents, the forward voltage can be very small. But as the current gets larger, it starts approaching, well, and exceeding this this sort of more nominal forward voltage of about 0.7 volts for your garden variety silicon diode. So let's talk about a few other kinds of diodes. You know, right here we've been talking about silicon diodes, but we have other kinds of diodes which are also very useful. So the first type of diode I want to talk about is called the Schottky diode. Schottky diode. The Schottky diode is constructed of a piece of doped silicon right up against a piece of metal. And I don't really know the sort of the physics of how it works, but you know, fundamentally the behavior is the same as a typical diode. Its symbol is a little different. We draw it like so. So its symbol is a little bit different. And there's some key points about it that are of interest to us. One, it has a lower forward voltage than its silicon counterpart. So while our silicon diode has a forward voltage of like 0.7 volts at appreciable current, a Schottky diode will have like, you know, 0.2 or 0.3 volts forward voltage. So it's much nicer in that sense. You get lower loss through the diode. The other nice property of Schottkys is that they're faster at switching. So what do we mean by faster at switching? Well, imagine that you have a PN junction, and of course it's forward biased. What if we apply voltage in the reverse direction? Like, or suppose we have I don't know, 10 volts applied in the reverse direction. Well, it's going to force a lot of these charge carriers, it's going to force a lot more holes into the N region and a lot more electrons into our P region. And it's going to, it means that if when we then flip the voltage around and forward bias it, all those charge carriers have to switch places in order for the diode to be forward biased. And that takes time. And that, maybe not, you know, on the scale of things, it's not much time. We're talking, you know, tens of nanoseconds, maybe hundreds of nanoseconds. But, you know, when you're doing fast switching, when you need things to switch very quickly, you know, from having a reverse voltage of, you know, some volts, 10 volts or something, to switching it, and you need to do that very quickly. Sometimes that's really necessary, and a Schottky is the only way to go. So while we're talking about reverse biased diodes, some diode parameters that you'll experience. Things like parameters of interest. One of those, of course, we talked about is the forward voltage. Another is what we just talked about. We call it the reverse recovery time. Another one that we care about is called the reverse breakdown voltage. Reverse breakdown. So this is kind of, you can imagine what this means. It means if we apply some voltage, some reverse voltage across the diode, there's a limit to this. There's some point where the diode breaks down, the junction breaks down, and it starts conducting in the reverse direction. So if we were to draw a graph, this is diode current, and this is, let's say, this is going to be, one sec. This is the diode voltage, meaning diode voltage at some point, you know, here at about 0.7 volts, we get this effect. The current starts increasing dramatically as the voltage goes up. We also have this effect where at some point way back here, we'll just call it V break, whatever. There's some voltage, some negative voltage, negative forward voltage, or i.e. reverse voltage, that will cause the diode to break down. Now, usually this is not a desirable effect. Usually this is sort of a, you could almost call it a failure mode. But there are diodes that make special use of this, and we call these Zener diodes. So what a Zener diode is, let's draw its symbol first. And I'm going to draw it like so. It's got these funny arms like this. A Zener diode, when your voltage is across it like this, it acts like a normal diode. You know, this is still anode, this is still cathode. But when the voltage across it is reversed like this, it's designed to break down at a very specific voltage, usually something, you know, fairly low. You know, for like a standard issue silicon diode, your breakdown voltage might be like 100 volts, but for a Zener, it may very well be like 5 volts or 15 volts, or something, some low value. So its graph is the same as our plot over on the left here, except that it's got a very specially defined breakdown voltage. So we would call that the Zener voltage. So Zeners are great for providing a precise voltage reference, for example, or for actually absorbing transient voltage spikes if you need to make sure that some voltage rail is always below some particular voltage. Those might be some use cases for those. Yeah, so that's a Zener diode. Again, the Zener voltage or the reverse voltage is dependent on current. So if this is a plot of, see, I want this to be my VZ, say I'll call this VZ, and this is IZ. For very low current, my Zener voltage is going to be very low. And then there's going to be this point, which we call the sort of the Zener knee, because it's shaped, this plot is shaped like a knee. This point about here, where the current is sufficient that the Zener sort of enters this, it enters regulation, we could say. So if our Zener voltage were like 3.3 volts, say, that's the point we want to reach. And you need to supply it with enough current to keep it at this desirable voltage. If you don't give it enough current, you can see its voltage is not going to be 3.3 volts. So this is an important graph that you'll find, or an important plot that you'll find in Zener data sheets. So let's move swiftly forward to the world of transistors. And specifically, we're going to talk first about the bipolar junction transistor. Bipolar junction transistor. And we abbreviate this as BJT. So taking what we know about doped silicon, let's say we had a region of N-type silicon, a region of P, again up against a region of P-type silicon, then up against another region of N-type silicon, and then connect ourselves some wires off each of these. Now, if you dope these correctly and you structure everything correctly, you can make a device such that when you pass a small current through this PN junction, then a large current will flow from this region, through this region, through this region. So that's the magic of BJTs. You can take a small current through this PN junction here, and it will allow a large current to flow through the device vertically like this. And so what we would call this down at the bottom the emitter. The reason being is because it emits electrons upwards into the device, right? If you have current flow, conventional current flow going the way it's drawn, then that means you have electrons moving, in the reverse direction of the conventional current flow. So this region here emits electrons to the rest of the device. We would call this terminal the base, And this terminal up here we call the collector. I don't actually know the reason for those terminologies, but those are the terminologies. We call the top the collector, base, and emitter. And this would be called an NPN BJT. And its schematic symbol is like this, where this is the collector, emitter, and base. And so in a BJT, the emitter is always drawn with an arrow. So you could think of it as the direction of the current flow that you're using to turn the device on. So we can also have the inverse of this. We could have P-type junction with an N-type sandwiched between them. We'll call this the base. We'll call this one we'll call the emitter. This time, this one will be the collector. And suppose we want to pass a small current through this PN junction. It will permit a large current through this direction. And so this gives us the PNP BJT, which we draw like this. And again, the side with the arrow on it is the emitter side. But this time the emitter is pointing inwards towards the device because that's the direction that it's funny, because the electrons are actually traveling, from the N region to the P region. But this region here is it's emitting electrons. It's weird terminology, I guess. I'll admit it. So, but this is the terminology. This is the convention. I like to draw a circle around my BJTs. Yes. So you may be wondering at this point, this device looks symmetrical. Like we have this base here. What's to stop me from passing, current from base to collector and having that permit a large current from emitter to collector? Well, the truth is there's nothing stopping you from doing that. It will do that. But the difference is that the gain that you experience is going to be much, much lower. So yes, that will work, where it will act like you think it does, except the gain is going to be much smaller. And so this gain that we're talking about, this gain is something we call beta. And this is equal to the collector current divided by base current. And for a garden variety BJT, this is on the order of about 100, but it can be anywhere between about 50 and 300 for your standard issue silicon BJTs. So if I've got myself a BJT here. Let's just draw this as ground, because often it will be. And if I trickle in current into the device, I base, then what kind of current can I expect into the collector? And that's how the BJT works. So you can see that my I collector equals I base times this beta number, which is, let's say it's 100. So if I want 1 milliamp out of, flowing into my collector, then I only need 10 microamps flowing into my base, which is great. So there the BJT acts like an amplifier in that sense. You have the same relationship with a PNP. They also have a beta and you pull current, but with a PNP BJT, let's say this time I'm going to tie this to a voltage source and you tie this to some load. Then if I pull current I base here, then this time I would say what is my, well, you still say what is your I collector. Now you can imagine if my base current I base is really, really small, I can make the equivalence of saying, because I emitter equals I collector plus I base, this is approximately equal to I collector. So that's a very, very often used and sort of engineering approximation that we can make, is that I emitter is approximately equal to I collector, because the base current is just so small. And so we have the same thing here, but I collector is beta times I base. So there's a rundown on BJTs. Before we move on, just worth noting, because you have this PN junction between base emitter, the current through it actually matches, it follows the Shockley diode equation, just like a silicon diode. Just like a silicon diode, you have this 0.7 volt junction, or if you have very small current, you have a very small voltage there. But for any sort of appreciable current, above a few tens of microamps, perhaps, it'll start to converge at around, between 0.5 and 0.7 volts. So between here and here, we could call this VBE, V base emitter. Likewise here, we have VBE. And VBE is about, let's say, 0.6 volts, because it'll be between 0.5 and 0.7, somewhere around there. If you want to know the exact voltage, forward voltage of the PN junction there, you got to use the Shockley diode equation. But often you don't have enough information, often you don't care enough to use the Shockley diode equation. This is a good enough approximation. So often what's useful, you can use the BJT for many things, but let's take an example where we want to drive, some kind of load. I'll call this my load. And I'd like to say power it from some VCC. But I only want to power it when I give it a signal to turn on. So here we can use, this is an example of using the BJT as a switch instead of as, an amplifier where you give it some amount of current and then it provides you with that amount of current or times beta. Here we just want to switch on a thing. So if you know your load, if you know what kind of current the load requires, let's say the load needs 100 milliamps. That's not unreasonable. But because I know beta is on the order of about 100, say, I know that I need at least, 1 milliamp going into the base so that I can get 100 milliamps from collector to emitter. So say I have an Arduino over here, and it puts out 5 volts, and I know that I need a milliamp going into this, at least a milliamp, because your beta might be less. And what we want to do is we want to really make sure that this BJT is turned on. We don't want to risk, not giving it enough current. What if your beta is 80 instead of 100? It'll vary between different batches of transistors. So you've got to make sure that it's getting enough current. So I know that my VBE, let's say it's about 0.7 volts. And I know that I can't just directly drive the base of this, BJT because of this diode junction. If I try to just drive it at 5 volts, then the current that would be required to actually achieve that would be really huge, and something would blow up. Either the Arduino would blow up or the PNP BJT would blow up. So what I do is I add a resistor here between my Arduino and my BJT. And I know now that the voltage across it is going to be about 4.3 volts. When I switch the Arduino pin high, it becomes 5 volts. And here we have 0.7 volts. So I know I've got about 4.3 volts. And I know I need about 1 milliamp. So if we do the math there, we can figure this out with Ohm's law, right? R equals V over I. So basically this is 4.3 times 1,000. That's a 4,300 ohm resistor, which, might be a little tough to find, but one that is fairly easy to find on this, all things considered, would be about a 4.02 kilo ohm. Why not 4 kilo ohms? I don't know, but this is a little more common to find 4.02K. So I'll make that resistor 4.02 kilo ohms, and we'll get a little bit more than a milliamp, and we'll make sure that BJT is really turned on, and you can power a load. So there's an example of using a BJT as a switch. So now I want to move straight on to MOSFETs. Now, MOSFET is another type of transistor. MOSFET stands for metal oxide semiconductor field effect transistor. Now, there are other types of field effect transistors that we're less interested in because we like MOSFETs, because they're easy to make and cheap to make, and they have a variety of other nice properties that you might learn about at some point. So we like MOSFETs. The way a MOSFET is constructed is, let's take a piece of substrate made out of P material, P-doped silicon. And then in it, we're going to cut these channels. Let's say our channels are made of N-type silicon, cut into the P material. And say I connect a wire here and a wire here. Then let's say I make this little layer of insulator, maybe like silicon dioxide or something. Then on top of this, I'll put a layer of metal. And I'll connect a wire to that. Now, what would happen if I were to apply a voltage between my gate, well, I'm going to call this the gate, spoilers. And let's call this the source. And we'll call this the drain. The terminology might make sense in a moment, or it might not, but we'll see. So say I apply a voltage between the gate and the source. And just by the virtues of its construction, the source is usually tied down to this metal substrate on the back below the P channel stuff. So the source is usually tied down to that. Okay, so I start applying a voltage between gate and source. And it's going to create an electric field in this dielectric that's going to repel positive charges. So it repels the majority carriers, and it pulls electrons to the surface and forms this channel because we have a surplus of electrons in our N material. Now we have a surplus of electrons in this P section because we applied an electric field here. This is going to become conductive because you have a surplus of electrons is going to become conductive. And we can now pass current from drain to source. That's the magic of a MOSFET. This is what we would call an N-channel MOSFET, because there are channels of N-type material cut into a P-type substrate. So we call these N-channel MOSFETs. So I'll draw the symbol for this now. So this is our source, this is our drain, this is our gate. Now this is a little incomplete. I'm gonna actually correct this. There's one little intrinsic sort of built-in component, which is a diode pointing from source to drain. That's our N-channel MOSFET. So when I apply a voltage between gate and source, we'll call it VGS. There's a threshold I have to reach before it will start conducting. But once I pass that threshold, I will start passing current. I will be able to start passing current from drain to source. And so this can act, analogous to a BJT, where with the BJT, you vary the current going into it, and that varies the current through it. In this case, we vary the gate source voltage, and that varies the current going through it. And so just like with the BJT, we have our P type or P channel counterpart. Our P channel counterpart is like the inverse of the N channel, and its operation is also the inverse. So let me draw for you the symbol. Make it as messy as possible. This time, this is our gate, this is our source, and this is our drain. What needs to happen now is I have to apply a negative gate source voltage. If this is positive and this is negative, VGS has to be less than 0 in order to turn it on. I have to drop gate below source. I have to drop gate below source in order to turn on my MOSFET. And we also see that the diode, the intrinsic or built-in diode, is flipperood. It points from drain to source instead of source to drain. Kind of makes sense. And the more negative VGS allows a higher I current from source to drain. Usually you express it as a negative drain source current, which is kind of goofy, because obviously if you draw it this way, where you say it's source drain current, then it's a positive current. It's just conventions. So those are our MOSFETs. So MOSFETs also can act as a switch, just like with our BJT. So let's say again, I'm gonna have a little setup where I've got an Arduino and I have some kind of load. This goes up to VCC. And I've got all this nonsense to draw that. And you can see we've made our circuit way simpler because we don't have to limit the current going into the gate because there is no current. There's no current required to keep the MOSFET on. So we can just connect this directly. And when it's at 0 volts, you have 0 volts gate source, the MOSFET is off and the current is 0. But when VGS here exceeds my V threshold, then the current starts going up. Well, I mean, it starts increasing, and the switch is on the load. So for this is so MOSFETs are nice. You don't have to have that. Oops, you don't have to have that that resistor limiting gate current. You can just have an Arduino switching a MOSFET and switching on and off a load. All right, so I think I'm not going to get super heavy duty into the theory or the math behind BJTs and MOSFETs, because that's, I think, a lecture for another day, and this has already gone on long enough. So with that, I think I shall call it a day, and thanks for watching.